Hello guys, welcome to another video. And in this video, I'm going to just go ahead and summarize what I have learned before and everything I have gone over on my YouTube channel for the CCNP security um, certification that I'm trying to take. And this is for the SIMOS certification for the CCNP security. And since I went on vacation, I kind of forgot everything I learned. I went on a 7-day vacation. And when I came back, I'm like, oh man, I don't really remember anything I have learned before. So I just want to go back and briefly go over some of the points or some of the videos that I have created before. So let's go ahead and start. And I'm going to start with the GET VPN, which was the first video that I created for the CCNP security certification. And as you can see right here, GET VPN is an um, iOS Get VPN is a tunnelless VPN technology that provides end-to-end security for network traffic in a native mode and maintaining the fully meshed topology. So it preserves the original source and destination IP address information in the header of the encrypted packet for optimal routing. So this is good. Hence, it is largely suited for enterprises for an enterprise running over a private MPLS IP-based core network. And GetVPN deployment has primarily three components. The one is the key server, one is a group member, and the other one is a group domain of interpretation, uh, which is also called the GDOI protocol. And the key server is responsible for maintaining the security policies, for authenticating the GMs or the group members, and providing the session key for encrypting traffic. The key server authenticates the individual group member at a time of registration. And there are two types of keys that the group member will receive from the key server. And the first one is the key encryption key, which is the KEK, and the traffic encryption key, which is also called TEK. And the TEK becomes part of the IPsec SA, with which the group members within the same group encrypt the data. And the KEK is used to secure the rekey message between the key server and the group member. So the traffic key, what it does is with this key you can authenticate the connection between the two endpoints, and the key encryption key is the one that lets you um, rekey whenever the TEK expires. You're going to be able to use this one to get another TEK. And the group member registered with the key server to get the IPsec Security Associations, the SA that is necessary to encrypt the data traffic within the group. And the GDOI protocol is used for the group key and group SA management. The GDOI uses Internet Secure Information Key Management Protocol, ISAKMP, for authenticating the GMs and the KS. And here's a picture of how that works. Um, you can see right here the first step that happens is the registration with the key server. So step one, right here they're registering with the key server. And then on the blue, which is the part number two, the normal get VPN operation. So whenever you are going to, what happens is with get VPN, they are all in the same group. So they are able to send encrypted data between all of them. So it's not like we have one link. It's like we have a cloud and they are all connected together and they are all able to talk to each other. So you don't have to create a different like interface for each one of them. So you don't have to create like one for this from this router to this router, and one from this router to this router, and from this router to this router. You can use just one interface to communicate with every single one of them. And then also the step number three is the rekey. And to get that rekey, remember you guys have to use the KEK key. So now let's talk about IKE version 1. And IKE stands for Internet Key Exchange, is the protocol used to set up a security association or SA in the IPsec protocol suite. IKE builds upon the Oakley protocol and ISAKMP. And IKE builds upon the Oakley protocol and the ISAKMP. So IKE comes in two phases, phase one and phase two. Um, in phase one, you can run in two different modes. The first one is main mode, which is the default mode, and the second one is aggressive mode. In this one's supposed to say in main mode, usually seen in site-to-site VPN connections, this is a 3 bidirectional messages exchange or 6 unidirectional messages. The first 4 messages are in clear text, and the last 2 are encrypted. And they do that because they want to protect the identity of the endpoints. In aggressive mode, which is usually seen when you are configuring a remote access VPN, it only uses 3 unidirectional messages. The last message is encrypted, but it's not mandatory, and this is due if you want to have the identity of the endpoints protected. That's when you want to use. That's when you want to encrypt the last message. And in phase one, um, negotiation, what you're going to negotiate is the authentication, where you can use a pre-share key, or you could use a signature, an RSA SIG or RSA ENCR, and then you also need to do encryption. And these four settings right here needs to match. So authentication needs to match, encryption needs to match, either DES, 3DES, or AES. The hashing algorithm needs to match, either ND5, SHA-1, or SHA-2, and Diffie Hellman group also needs to match for phase one. And the other parameters that you have to configure but do not need to match are the SA lifetime, which is in seconds, um, and it is negotiated to the lowest value between the VPN peers. So the SA does not need to match, but it cannot be higher than the one um, than the other ones. If the other endpoint is providing the lifetime, you cannot be higher than that. You could either be equal or you could be less than the other endpoint. And in phase two, the scope for the phase two is to negotiate the scope of the IPsec tunnel. And what you want to do is you want to protect, um, and the scope is what you want to protect and how you want to protect. That's what happens in phase two. And upon successful negotiation, 2 additional keys are derived from phase one, key material by default. You could use, unless you're using PFS, which stands for perfect forward secrecy. Um, so if PFS is enabled, then you are not going to get those additional keys. And these 2 keys are used to encrypt data through the IPsec tunnel. And phase two only runs in one mode, which is quick mode. In phase one, so that you are either running main mode for site-to-site VPNs or aggressive mode, which is for remote VPN connection. And quick mode uses 3 unit directional messages secured through keying material of phase one. So the scope of phase two is to just protect phase one. And here is the parameters that you want to negotiate in phase two. The first one is what you want to protect, and here what you're going to do is create either a proxy ACL or an encryption domain, either of those. So on my videos, I have done this where I create an ACL, which is what I want to protect, what network I want to protect. I put it here on the proxy ACL, and then how I want to protect, which is using the transform set. And here, this needs to match with the other endpoint, so the encapsulation protocol. So if you want to use ESP, which provides everything, it provides authentication, integrity, and encryption. And AH, which does not provide encryption, it only provides authentication and integrity in anti-replay. ESP also provides anti-replay, but AH does not provide integrity encryption. And the encryption that you can run is either null or nothing. DES, through DES, AES, AES GCM, or AES GMAC. And the hashing algorithm so you can run on this phase 2, MD5, SHA-1, or SHA-2. And the tunnel mode also needs to match either tunnel or transport with or without UDP. The negotiated parameters that do not need to match again is it the lifetime, and the lowest values are negotiated, and highest values needs to initiate the tunnel. So here is how the authentication header encrypts the packet. So the authentication header protocol provides data origin authentication, data integrity, and entry replay protection. So as you can see right here, it does not provide data encryption. So however, AH does not provide data confidentiality yet because it does not provide encryption, which means that all of your data is sent in clear text. So it only uses the way that the AH does it is that it provides the hashing algorithm, and then it adds a pre-shared key to this packet. And here how it does it. Here's the original packet. What happens is that um, the AH header is inserted between the IP header and the TCP header, and that's how the authentication header works. And for ESP, which is more stuff, and we also have two modes, which is either transport mode or tunnel mode. And as you can see right here in transport mode, what happens is that we insert the ESP header between the IP and the TCP, and the trailer between the data and the ESP authentication. All right, so we insert this one, two, three packets when we use an ESP with transport mode. But as you can see right here, we do not, um, we are still using the same IP address. So the true source and destination IP address is going to be none. But when we use tunnel mode packets, we actually encrypt the IP, the true IP source and destination address. So whenever somebody intercepts these packets, they won't be able to know where it's coming from because we have created a new IP header right here, and this happens in ESP tunnel mode. And you can see right here why to use AH with ESP. So you can also use AH with ESP, and if you take a look at this, you can see how it works. So if you want to post a video and take a picture of it, you can go ahead and do that. So now let's go ahead and move on to IKE version 2 since we already talked about IKE version 1. And in IKE version 2, like IKE version 1, it still uses UDP 500. And if we are using NAT, we are going to use the port number 4500. It has the same scope and goal as IKE version 1. It's just a little bit better and a lot faster. And it's not backwards compatible with IKE version 1, so you cannot have an endpoint configured with IKE version 1 and the other endpoint configured with IKE version 2. They both need to either have IKE version 1 or IKE version 2 configured. And the changes is that for IKE version 1, they created additional RFCs and are not even a standard. They're now built into the main RFC. So before, a long time ago when IKE version 1 came out, there were a lot of vulnerabilities that they were found. And what they did was that they just created um, additional RFCs like ISAKMP was created, AH and ESP was created, IPsec with DOI was created, DPD was created, NAT-T was created, and mode config was created just so they could fix IKE version 1. But for IKE version 2, all of this is in just one RFC, which is IKE version 1 RFC. So what are the phases of IKE version 2? So IKE version 2 runs in a single phase, and it only does it on this, and it's basically just phase 1. And what it does is it has this IKE SA init, which is the ISAKMP, and then IKE authentication, which is the IPsec or transform set um, configuration. And there are also some optional messages that you could have, which is the create child SA and the informational message. And for the phases, or it's not phases because it's only one phase. I should change that to just phase. This is how it works, just one phase. So on here, what happens is the IKE version 2 Security Association establishment. This is where they propose the selection and the key exchange. And then for the other one, which is only in phase one, they're both are part of just phase one because there's only phase one, there's only one phase in IKE version 2. So in IKE authentication, mutual authentication and identity exchange, the initial IPsec essays establishment, the certificate exchange, which is optional because you can use a pre-share key, and the configuration exchange is also optional for IKE version 2 phase. And in IKE version 2 authentication happens in IKE underscore authentication step. So IKE version 2 supports asymmetric peer authentication, and that means that different pre-share key for pre-share key authentication. So you can have a pre-share key of 123 on one side and another pre-share key of ABC on the other side. So one side using the pre-share key authentication and the other side using pre-share key authentication. So there you are able to use two different pre-share key authentication for them, and that means that we are supporting asymmetric peer authentication, which uses two different keys. And also here are the VPN types supported for IKE version 2. CryptoMap, which is only, this is still around because the ASA or the firewalls, the Cisco firewall still supports only this option, which is dinosaurs time. It is not recommended, and it was kept for inter and it was kept because the ASAs are only able to do this. So if you want to configure a VPN tunnel, site-to-site VPN tunnel between the router and a firewall, you have to create a crypto map. But if you are configuring a IPsec tunnel between two routers, you do not want to use a crypto map. You either want to use GRE with IPsec on top of it, SVTI or DVTI, DNVPN or GET VPN. Okay, so now let's go ahead and talk about FlexVPN. It's a just cool name. What is FlexVPN? So Flex VPN is a common umbrella for all IKE version 2 IPsec VPNs deployed on iOS routers. And it has technical benefits, but it's also a marketing term. So the technical benefits of FlexVPN is that um, you are going to use a template for all VPN types. So you no longer need to remember 50 plus templates of VPN configuration. Um, so like for like GRE with IPsec, SVTI, DMVPN, or GET VPN, you do not have to configure them differently. They all are going to be almost identical because you're going to use a template which is called FlexVPN. So FlexVPN is just a template for all IPsec for all IKE version 2 IPsec VPN deployment. And it is based on each VPN type, and some additional extra configuration templates are required, but not like a big configuration um, for all different VPN types. And here how it is, I'm going to give you some of the blocks of how it is configured. So you're going to first build a proposal, and this is mandatory. And in IKE version 1, this was called the ISAKMP policy. It defines It's defined with name and not a number anymore, so that's good. So you can name as many proposals as you want, and you can give it a name that you could remember. So this is a lot better than just a number. And by default, there is one that is always going to exist. Um, so IKE version 2 proposal configuration, you are going to encrypt like always, with multiple entries can be configured, which is really good. Integrity, and you can also do multiple entries, and Diffie Hellman group, which you could also do multiple entries for this. And IKE version 2 proposal no longer contains authentication method or SA lifetimes. And after you build that proposal, then you're going to create the policy, which is also mandatory, and it needs a IKE version 2 proposal attached to it. So whenever you create the proposal, you're going to attach that proposal to the IKE version 2 policy. And by default, one exists, and its scope is to control which proposal is used per IPsec VPN tunnel. IKE version 2 policy configuration, um, where you're going to configure there is that the first thing that you want to do, so you don't forget, is to attach the IKEv2 proposal. You either going to, which is optional, you can add the terminating local address for the IPsec VPN, and also you can either add the FVR or the FVRF, which is also optional. And this is the way that works is we are isolating the transport network, or whenever you're using the FVRF is when you are like isolating a transport network, usually facing the internet, and this allows us to configure the default route that won't interfere with routing with the routing table in our global table. And proposals are attached to the policy. So remember that. So if a proposal one is attached to policy one and the peer choose to use policy one, the peer will use the proposal one because it is the one attached to that policy, if that makes sense. And now let's go ahead and take a look at how CryptoMap and the IPsec profile works. So the CryptoMap and the crypto IPsec profile are one and the same. Um, there's one that is the legacy way, which is the CryptoMap, and the new way, which is the profile of configuring IKE phase 2. So in CryptoMap, you need to specify how to protect traffic, which is the transform set, and what to protect, which is the ACO, and what is the remote VPN peer. That's what you do it in the CryptoMap. In the IPsec, the same goes if you use IPsec Profile, where you need to specify how to protect the traffic, which you're still going to use the transfer set, and what to protect, which no longer requires an ACO. So a IPsec profile is just based on routing calls. IPsec profile is always applied to a GRE or VTI interface. Thus, you have a logical interface associated with the IPsec tunnel. The remote VPN peer is no longer specified as it is one and the same as the GRE or VTI tunnel destination. It can be um, configured statically or dynamically learned. And here's the configuration between the profile and the tunnel. So as you can see right here, side to side, the side to side configuration. This one right here is for the profile. This one is for the crypto map. As you can see, we are going to create a transfer set. That's the first step that we do. And for the crypto map, the first step that you do is to create the extended access list and permit what you want to protect. And then you go ahead and configure um, the transform set over here, and that's the first step that you do for the profile. And then you give it what you want, how you want to protect, which is using the mode tunnel, which you also do it for the crypto map. But then we are going to create a logical interface or GRE tunnel right here, as you can see right here. And then after you do that, you're going to attach that tunnel protection IPsec profile, and then you give it that name of the profile that you want to use, which is the one that we create over here. But for the crypto map, we do not do it like that. And you will only use the crypto map for IKE version 2 is whenever you are trying to configure a IPsec site-to-site IPsec tunnel between a router and a firewall or ASA. If it is between two routers, then you want to use a profile right here, which this one is using a tunnel or GRE tunnel. So what is like the difference between GRE with IPsec versus SVTI, which they are really, really similar. And it's only one command that actually gives it away. So let's go ahead and start with GRE. So GRE is a tunneling protocol developed by Cisco. It is capable of encapsulating a wide variety of network layer protocols packets inside IP tunnels. This creates virtual point-to-point links, and it is a common option to use GRE to pass dynamic routing protocol traffic across an IPsec tunnel. So GRE do not provide um, encryption services. GRE is just an encapsulating protocol. It does not offer other services such as encryption. By default, the traffic leaves in clear text, which is why you attach IPsec to it, so you can encrypt the traffic. And here how it works whenever you are using GRE with IPsec. So however, IPsec does not directly support IGP protocols because the IPsec tunnel cannot natively forward IP4 multicast. And to overcome this, what we do is we can use a GRE tunnel that actually runs over the IPsec tunnel. And GRE supports multicast by encapsulating them in a unicast packets. So GRE supports IGPS, which is why you want to use GRE with IPsec because GRE does not provide encryption, but IPsec does provide encryption. IPsec does not support multicast, but GRE does support multicast. So here how it works, you are going to the running the protocol updates. So this is means that we are using GRE, or actually we're using the routing protocols. If we want to use IGP or EIGRP or SPF or any of those, so that goes into the GRE tunnel. So since the GRE tunnel provides the multicast, we are going to use the GRE tunnel so we can do the routing protocols updates. But since GRE does not provide data encryption, then we're going to just put an IPsec crypto map or IPsec profile on top of GRE, and that's going to encrypt the traffic and also route the traffic because it is able to support multicast. And here, this is how it works. So here's the passenger protocol. If you're using IGP, RGRP, or SPF, or any of those routing protocols, what happens is it is encapsulated into the GRE tunnel. So we just insert a GRE protocol right here, and then since we want to encrypt this, because we don't want to send it via, we don't want to send it via clear text. What we do is we just put IPsec on top of it, and what happens is that right here, since we're using a transport protocol, you can see that it is inserted inside IP, GRE, the original IP packets header, the TCP, and the data, and we put those in between the ESP header and the ESP trailer and the ESP authentication, and then we just create a new IP UDP header right here because we're using the transport mode for ESP. And for SVTI, so a major benefit of VTI is that the configuration does not require static mapping of an IPsec session to a physical interface. So the IPsec endpoint is associated with an actual virtual interface. This is then a routable interface at the tunnel endpoint. And many common interface capabilities can be applied to the IPsec tunnel. They include the association of routing protocols and therefore routing across the VPN tunnel. In the end, VTI is a good alternative to IPsec over GRE tunnels. And the advantage of using VTIs as opposed to cryptomap configuration is that users can enable dynamic routing protocols, like I said before, on the tunnel interface without the extra 4 bytes required for GRE headers, thus reducing the bandwidth for sending encrypted data. So what happens is whenever we use SVTI, we dropped that 4 bytes required for GRE headers. So let's go ahead to the next slide. Yes. So on the next slide, as you can see, the only thing that this is the same as using GRE. I mean, we are using GRE, but when we use SVTI, we just drop that 4 byte um, packet whenever we are using SVTI with IPsec. And as you can see, we just drop that 4 byte. We makes that packet a little bit lighter, and therefore it is a lot faster to use SVTI instead of just GRE. And that is the main benefit of using SVTI. And here's we are comparing the configurations of um, either using SVTI or just GRE. And let me see if I can find the only difference because they're all the same. And the main difference is that, let's see if I can find it. So in the interface one, we're using the source, destination, um, The tunnel mode, we use IPsec right here, IPsec over IPv4. So this is how you configure for SVTI, and this is how you configure for GRE. So whenever you use this one, this command right here, tunnel mode IPsec IPv4, we are removing that 4 bytes of the GRE. But if you use this tunnel mode GRE IP, it is going to add that GRE 4 byte packet into the header. And GRE is clear text. GRE has multicast. GRE does not support dynamic routing. SVTI supports dynamic routing, OSPF, EIGRP, RIP, and BGP. SVTI drops GRE 4 bytes header, and SVTI has multicast. So that is the summary of GRE versus SVTI. So I think I got confused. I said that GRE supports dynamic routing protocols, but I guess it does not. So SVTI is the only one that supports dynamic routing protocols. So that's why you want to use SVTI instead of GRE. And this is it for this video. I feel like I now remember a lot more um, than 8 days or 7 days ago when I left for my vacation. So this was a really good summary. So on the next video, what I'm going to do is I'm just going to create a lab where I'm going to configure a GRE um, IPsec side-to-side tunnel, and also I'm going to configure a SVTI tunnel so you can see the difference between both of them. So thank you guys for watching this video. I hope you guys enjoyed this summary. Um, and I'll see you on the next one, guys. Bye bye.